Hello friends, have you ever wondered if a distant exoplanet have magnetic fields just like Earth? So join me today as I explore a groundbreaking method that uses our own moon to detect the invisible force field of the alien worlds. So in this video, which is how the moon helps us find the alien magnetism, we dive into the fascinating science behind using the moon as a giant cosmic shield to block solar wind interference, allowing us to pick up the faint radio signals emitted by the planet's magnetosphere. So when I say planet, it's basically the exoplanet. Let us explore further. So friends, welcome and if you are a space explorer, then you have reached the right place. And we are embarking on an incredible journey that stretches from our familiar moon to the distant reaches of the exoplanetary system. Today we are not just looking at the stars, we are delving into the invisible force that shapes alien world, their magnetic field, and surprisingly our own lunar neighbor might be the key to unlocking these secrets. For centuries, we have gazed at the moon, a silent sentinel in our night sky. It has been a muse for poets, a target for our first step beyond Earth, and now it is poised to become a crucial platform in our quest to understand planets light years away. How can this seemingly barren rock help us detect something as elusive as the magnetic field of alien worlds? That is exactly what we are going to uncover in the next few minutes. Before we explore the moon's role, let us understand why exoplanets' magnetic field are so important for us to understand in the first place. We live on a planet with robust magnetic field generated by the movement of molten iron in our core. This invisible shield called the magnetosphere is vital for life as we know it. It deflects the harmful charged particle of the solar wind and the cosmic rays, preventing them from stripping away our atmosphere and eradicating the surface, some amount of surface. Without it, Earth could have become a barren wasteland like Mars, which lost most of its atmosphere billions of years ago. So when we look at the exoplanet, the planets orbiting stars other than our sun, one of the fundamental questions is, do they have magnetic field? If they do, it significantly increases their potential to host life. A strong magnetic field suggests a dynamic interior, which can also be linked to geological activities that help regulate planet's climate. Detecting these fields is like finding a vital piece of puzzle of the planetary habitability. By detecting something as intangible as magnetic field across the interstellar distance is an immense challenge. Exoplanets have increasingly faint and they are quite far away, making direct observation of their magnetic field next to impossible with current Earth-based telescopes. The signals we are looking for are often very weak and easily drowned out by the noise of our planet's electromagnetic environment. So, as well as the interference from the sun and vastness of the space itself. Traditional method for studying the exoplanets often focus on observing the slight dimming of a star as a planet passes in front of it, which is also known as the transient method, or the subtle wobble of the star caused by the gravitational pull of the orbiting planet, which is also known as the radial velocity method. These techniques tells us about a planet's size, mass, and orbit, but they don't directly reveal the presence of its strength of the magnetic field. Scientists have tried indirectly infer the magnetic field by looking for auroras on the exoplanet, similar to our northern and southern lights. Auroras are created when charged particles from star interact with planets, magnetic field, and atmosphere. However, detecting these faint auroral emissions from light years away, it's quite incredibly difficult and requires extremely sensitive instruments. This is where our moon enters the picture as a game changer. What makes moon such a promising platform for detecting exoplanets' magnetic fields? Several key factors come into play. Firstly, the moon has no significant atmosphere. Earth's atmosphere, while is crucial for life, also distort and absorb electromagnetic radiation, including the faint radio waves that might be emitted by the exoplanet atmospheres. The moon lack of atmosphere provides a clear, unobstructed view of the cosmos across a wider range of electromagnetic spectrum. Secondly, perhaps most importantly, the far side of the moon is remarkably radio quiet, being permanently shielded by Earth's vast array of radio transmission from television and radio broadcasts to satellite communications, creating an environment with significantly less electromagnetic interference. This radio dark zone is an ideal location for building an ultra-sensitive radio telescope designed to pick up faintest whispers from distant exoplanets. Imagine a giant cosmic shield blocking out all the terrestrial noise, allowing us to listen for an incredibly faint signal emanating from the alien worlds. That is the potential of the far side of the moon that it offers. So, how exactly would lunar-based observations detect exoplanets' magnetic field? The primary method involves listening for a low-frequency radio emission. When a planet with magnetic fields attracting, with the stellar wind from its host star, it can generate these radio waves. The stronger the magnetic field and more energetic the stellar wind is, the stronger these emissions are likely to be. These radio waves, although weak by the time they reach us, can be detected by the sensitive radio telescopes. However, as we discussed, Earth's own radio noise makes it incredibly difficult to pick up these faint signals from the ground. Placing these radio telescopes on radio quiet far side of the moon would significantly reduce the interference, allowing us much more sensitive observation. Scientists are currently developing a concept for lunar-based radio telescopes. One promising idea involves deploying an array of small interconnected antennas across the lunar surface. This distributed approach would provide a large collecting area, enhancing sensitivity of the observatory and allowing it to pinpoint the source of these faint radio signals. While still in planning stage, the prospect of lunar-based exoplanet magnetic field detection is incredibly exciting. A future robotic mission to the moon could pave the way for deployment and operation of these advanced observatories. Imagine the discoveries we could make by this infrastructure. Detecting a strong magnetic field around a potential Earth-like exoplanet in the habitable zone of its star would be a monumental step in our search for life beyond Earth. It would suggest that the planet has the necessary protection to retain its atmosphere and potentially support liquid water on its surface for billions of years, and the conditions we believe are crucial for development of life itself.